Okay, sports fans, welcome back to another exciting session. So today we're interested in deciding whether or not a set of data could be modeled using an exponential rule. So you'll recall from the last unit, to decide whether data is exponential, we take successive outputs and divide. 256 divided by 64 is 4. 64 divided by 16 is 4. 16 divided by 4 is 4. And 4 divided by 1 is 4. So indeed, this is exponential, and R is 4. All right, so here's our next table. We want to know whether it's exponential or not. Just so you know, I'm using tables right out of your book, so if you want to pause the video now and go get your book, that'll be okay. We're on page 775 in your book, and this is table B. So, is this exponential? Is it not? So 25 divided by 19 is about 1.316 or so. 19 divided by 13 is about 1.462. 13 divided by 7 is about 1.857. And then last but not least, 7 divided by 1 is 7. And you can see that all four of those values are pretty different, so indeed this is not exponential. All right, here's another example. This is example D on page 776 in your book. So what about this? Exponential or not exponential? Well, as strange as these numbers look, it turns out that this ugly number, 0.00390,625, divided by 0.015625, is indeed a quarter. And this guy, 0.015625, divided by 0.0625, also a quarter, and these two also a quarter, and these last two a quarter. So indeed, this one is exponential, and R is 1/4, or if you prefer, 0.25. So would this be a growth or a decay function? All right, welcome back. Let's turn over to page 777. I don't know why I'm saying welcome back. You probably never went anywhere. Page 777, you'll see this table written out a lot more nicely than you see it on my screen, and it represents the population in the United States from the years 1790 to 1890. So what do you think, exponential or not? So to answer that question, we need to divide those populations and see if they all give the same value. So what I need you to do is take each one of these populations and divide it. So 62,979,766 divided by 50,189,209. Aren't you glad you have a calculator? So I'm going to pause the video and let you do all of these divisions. Please round your answer to 2 decimal places. And so I'll hang up and listen. All right, so that may have been the funnest thing I've ever done. Certainly we didn't get the same value for all of them, but you will notice that they're all relatively close. We got 1.25, 1.30, 1.23. You can read. So what might we do with all of those values to get an R value that was reasonable? And hopefully you said find the average. So that's what I want you to do next. I want you to average those R values. So add them up, and since there are 10 of them, divide by 10. Again, I'll hang up and listen. So hopefully you got what I got. I got an average R value of about 1.32. Now, let's think about our input. Our output is population. Our input is year. And each time we're going up by a decade. Well, what could we do to that to make it just go up by one, to make it kind of easier to think about? Well, we could think about decades. So let's write over here, decades since 1790. So if 1790 is our starting point, then how many decades after 1790 is 1790? Well, hopefully you said 0. And then 1800 would be 1 decade later. 1810 would be 2 decades after 1790. 1820 would be 3 decades since 1790. Hopefully you're seeing the pattern. So let's go and fill that out. Now, so let's think about how to write an exponential model. It's been f of n equals a times r to the nth. Well, A is going to be the initial population, and to make things easy, maybe we talk about that in billions. So for millions, excuse me. So 3,929,214. Maybe we just round that to 3.9 million. And then our estimate for R, remember we just got through averaging it. We said, hey, that looked like about 1.32 was a good average. And now let's make that x, and let's make this f of x. So at this point, what I want you to do is go to your calculator's statistics menu and type this previous table. For x, use the decades since, so 0, 1, 2, 3, and so on. And for the y values, or maybe you put those in list 2, let's use our population rounded to the nearest tenth of a million. So 3.9 million, 5.3 million, 7.2 million, 9.6, 12.9 looks like, and so forth and so on. So you'll have list 1 and list 2. These will be 0, 1, 2, 3, and these will be the rounded millions, like 3.9, 5.3, 7.2, 9.6, and I ran out of room, but you'll type all those in, make a scatter plot, and then type this in to the Y editor and see if that graph, that curve, matches your data. All right, so let's try these problems just to kind of get our feet wet. Page 786, let's do 1 through 4, and on page 788, let's do problem number 8. I'll see you next time.